So this lecture is going to introduce the concept of enthalpy. So we'll start off with a little bit of review and recall that when we talked about the first law of thermodynamics, it was this idea that the energy of the universe is constant. And we can write that for a chemical reaction where the change in energy of a chemical reaction is equal to all of the heat and work that are produced and released. Now, also recall that we talk about heat and work being produced or released from a chemical reaction. We have to think about their sign. And in general, and whenever an energy, whether it's heat, work, delta E, or later on delta H, if it's negative, if it's less than 0, that means energy is leaving our system. So when Q is less than 0, we say it's exothermic. If work is less than 0, we say work is done by the system. If these values are positive, so if Q is greater than 0, it's endothermic and the reaction is absorbing heat. And if work is greater than 0, then work is done on the system. Now, when we think about this first law of thermodynamics, and one of our goals is going to be to determine how much energy, what was the energy change associated with a chemical reaction. So how much heat or how much work was produced from a chemical reaction. And it's actually not a trivial thing to do. And one of the problems with that are heat and work are what we call path functions. And what we mean by that is if we change the reaction conditions in the way we run a chemical reaction, heat and work might change. They're dependent upon the conditions. Delta E is a state function in that it's not going to change. Delta E will be a constant for a chemical reaction. It'll always be the same, but the amount of energy that goes to heat and the amount of energy that goes to work will change. So this idea of a path function versus a state function, the common example and taken from your text shown here is this idea of if you were to climb a mountain, so you start at the base, you go to the summit, you can have two choices of path. You can do this green path X, or you can do this orange path Y and wind your way up to the top of Mount Kilimanjaro. The change in elevation from where you started, where you finished, is the same regardless of what path you take. So delta elevation is a state function. The only thing that matters is what's your final state and what's your initial state. But the distance traveled, the mileage it takes to get to the top, is going to depend on what route you take. So this is a path function. And so again, we're seeing that heat and work are path functions. And if we change chemical conditions, we can change the amount of heat, we can change the amount of work that's produced, but the delta E is always going to be the same. So chemists, in part due to this, have defined a new energy term, which we are going to call enthalpy. So enthalpy gets the symbol capital H. And whenever you see this, if you don't know what this means, this 3-bar equality, that means defined. So enthalpy has been defined to be equal to all of the energy and this factor called pressure volume. So pressure times volume. We'll talk about that in a second. So when we think about this, energy is a state function, and enthalpy is also a state function. So the only thing that's going to depend on enthalpy is your initial state and your final state. And the only thing that depends on energy is the initial state and the final state. Heat and work are path functions. When we think about how we can run a chemical reaction in chemistry, we typically think about it in two types of conditions. We can perform a reaction at constant volume, where we cap a chemical reaction and we make sure that the total volume of our container cannot change, or we run a reaction at constant pressure. So a constant pressure reaction is by far more common. This is usually just run a reaction and don't have a lid on it. So the constant pressure is just atmospheric pressure. Constant volume reactions are a little bit more problematic because if your reaction builds up pressure, you run the risk of an explosion taking place. In both of these conditions, the total change in energy of a chemical reaction will be the same. But again, the amount of heat and the amount of work produced will change. So delta E, total change in energy, is equal to Q plus W. And the work is equal to the negative exterior pressure times the change in volume. And we're not going to work with this equation, but the important piece to recall is that work is dependent upon if a change in volume occurred. That's how we would figure out work if you go on in chemistry. So if we just think about that for a second, and we consider the situation where we run a reaction at constant volume, well, delta E is equal to the heat produced in the subscript V is telling us it's at constant volume, plus any work. So delta equals Q plus W. But if we substitute in our work expression, negative P delta V, so delta E is now equal to Q sub V minus P delta V, but we know delta V is 0 because we're constant volume, so there's no change in volume. What that means is, at constant volume conditions, no work can be done. So if we run a reaction at constant volume, all of the energy has to go to heat. So at constant volume, all energy transferred has to be heat, and we have no work that can be done because we can have no volume. That's really important because if we run a reaction at constant volume, we know we can often determine the amount of heat that was produced, and we know the amount of heat produced in that is going to be the same as the total amount of energy change of that reaction. This is done most commonly using what's known as a bomb calorimeter. And this is actually the technique that's used to determine the calories in food. And so if you click on this link on the lecture PDF, you can watch a little video about this. Here's a picture of a bomb calorimeter. And in general, what happens is you take a tiny piece of food and you connect it to 2 electrodes in here. We seal this reaction up tight, and this cylinder is made to withstand huge changes in pressure. We're then going to pump this cylinder full of oxygen gas, and then we're going to cause a spark down our electrodes, and we're going to undergo a combustion reaction. So we're basically going to explode this small piece of food, and then we will monitor the heat that's produced, and the total amount of heat produced is equal to the total amount of energy that was in that piece of food. And again, because energy is a state function, this piece of food will give the same amount of energy if we burn it or if we eat it in our bodies. So that's how we can determine the calories in a piece of food. So this is all at constant volume. We could also run reactions at constant pressure, right? And I'm going to show you a derivation. You don't need to know this derivation, but I want to show you where things come from. So if we consider a constant pressure situation, so delta E equals Q sub P plus work. And remember, we've defined our function where H, enthalpy, is defined as energy plus PV. So now I'm going to substitute in for work. So the delta E is Q sub P minus P delta V. And we can just rearrange. So I'm going to move our negative P delta V. I'm going to add that to the other side of the equation. So now Q sub P is equal to delta E plus P delta V. And so now what we can see is delta H, the change in enthalpy of a reaction, is equal to the heat produced at constant pressure. And this is really the key. And this is where the enthalpy term really came from. If we measure the heat produced at constant pressure, that is equal to the change in enthalpy, right? And we know this change in enthalpy is 2 pieces. It's the total energy and it's the work. But the heat produced at constant pressure, we can now refer to as the enthalpy of reaction. And again, this is so important because heat is a work function, but delta H is a state function, so that we can often determine delta H if we know the enthalpy of the products and we subtract the enthalpy of reactants, final state minus initial state, we can determine the delta H, the enthalpy of a reaction. Or if we measure the heat produced, we know that heat produced is the delta H of reaction. And we'll see examples of this as we go on. So if we measure the heat change of reaction at constant pressure, we can find delta H. And we'll see examples of this as we go on in this lecture and further lectures. So we will often talk about enthalpies of reaction. So the enthalpy change, delta H, of a reaction is equal to the transfer of heat into or out of the system. So delta H equals Q sub P. We often report enthalpies of reaction is per mole of reaction. So if we just think about this for a second, if we consider an energy diagram for the combustion of methane, so our chemical reaction is CH4 plus 2O2 goes to carbon dioxide and 2 waters. And now I'm going to put energy here. So the other thing that comes out of this reaction is we're going to produce energy. So in our energy diagram, we have an initial energy state. When we run the reaction, we're going to go to a lower energy state to produce our products. And this is the amount of energy that is released. That energy is released, so it is a negative value. So if we can measure the amount of energy that's released, the amount of heat that's released from this, that's going to be our delta H of reaction. If we were to do this for methane, we could figure out that the delta H is negative 802 kilojoules. So that's an experimental value that somebody had to do. And the way we would read this is that this negative 802 kilojoules, this is the amount of energy produced if 1 mole of CH4 reacted with 2 moles of O2, right? So this amount of energy is really a per mole of methane or per 2 moles of O2 based on our chemical reaction. So we could go through a couple examples of some calculations. So here's our first example. And say how much energy is produced if 25 grams of methane are burned in excess O2. So again, this is the amount of energy produced if 1 mole of methane were reacted. So now we have 25 grams. So our first step is going to be to convert grams into moles by dividing by the molar mass. So now we know how many moles of methane we have. So now we're going to take the moles of methane and we're going to go through a conversion. So we're going to start with the moles of methane, and we're going to multiply by negative 802 kilojoules per mole. And notice the negative sign, it's negative because energy was released. Right? So when we multiply these, we get negative 1,250 kilojoules. So if we were to burn 25 grams of methane, we would release negative 25 kilojoules of heat. So let's try one more problem. And in this problem, we're going to start with 0.05 moles of HCl and react that with 0.05 moles of sodium hydroxide to form sodium chloride and water. And if we perform this reaction, it was measured that 2.9 kilojoules of heat are produced when we react 0.05 moles of HCl with 0.05 moles of sodium hydroxide. So now the question is, what is the enthalpy change per mole of HCl? All right, so this is sort of the reverse as the previous problem. So to answer this, we have to think about that if we react 0.05 moles of HCl, we get 2.9 kilojoules of heat. Now we want to normalize this to figure out how much heat would be released if we had a full mole of HCl. So what we're going to do is we're going to divide the heat by the moles of HCl used in the reaction. And so we have negative 2.9 kilojoules divided by 0.05 moles. And again, watch that negative sign. It's negative because this is exothermic. And we divide this out. We get negative 58 kilojoules per mole. Thank you.